In this video, we look at a slight variation on the common source amplifier configuration. Instead of the source being grounded in this configuration, as it was in the common source, we've inserted a resistor between the source and ground. We're going to call that R sub S. It turns out that R sub S provides some negative feedback that stabilizes the bias configuration. We can understand that by realizing that any voltage drop across R sub S is going to reduce the voltage will reduce the voltage between the gate and the source. So for example, if something were to happen to cause the current through the transistor to increase, in other words, I sub D were to increase, the resistor here would have the effect of raising the voltage at the source, thus reducing the gate to source resistance, or the gate to source voltage, which would have the effect of reducing I sub D. So the effect of an increasing I sub D raises the voltage at the source, which reduces the gate to source voltage, which then feeds back in a negative way to constrain the original change. Thus this R sub S is useful. One of the reasons the R sub S is useful is it provides that negative feedback to stabilize the biasing, the biasing configuration, or the biasing state. Next, notice that when we replace the transistor with a small signal model, we're using the T model rather than the hybrid pi. This is useful because in the T model, the resistance seen looking back into the source, this 1 over G sub M, ends up being in series with R sub S, and it makes for the analysis significantly easier? Yeah, it makes the analysis easier by having those two resistances in series. Next, note that this series combination here, those two resistances, makes it so that the voltage that's amplified coming into it is not the full signal. We've got a voltage division across 1 over G sub M and R sub S. Thus, VGS here, plus to minus, the voltage from the gate to the source, is a subdivided portion of Vin, or V sig, and we get then that VGS is equal to Vin times, and we're taking VGS as the voltage across the 1 over G sub M resistance, so it's 1 over G sub M divided by 1 over G sub M plus R sub S. So there is a reduction in the there's a voltage division at the input causing a reduction in the signal to what is actually being amplified, or that the signal being amplified is a reduced amount of the original signal coming in. You'll notice that if R sub S was 0, in other words, we had the common source configuration, Vin would equal, or VGS would then equal Vin, and we wouldn't have that division. But that source resistance does cause a reduction in the gain. Finally, we're going to remit the early effect resistance, the little R0. That resistance would be connected between the drain and the source and significantly complicates the analysis. It turns out that R0 doesn't have as great of an effect in this configuration with the source resistance there, and so the results that we'll get are still going to be valid to a large extent, not affected by eliminating that or neglecting that early effect resistance. So with these observations, let's go ahead with characterizing it. I believe we've already mentioned that because the source is still connected to the gate, the input resistance is still infinite. Once again, we can get the output resistance R out by deactivating the source, which then causes this current source here to be 0 in an open circuit, and looking back in, again noting that we've neglected the little R0, the early effect resistance, we have then that R out is just the drain resistance. To determine the open circuit gain AV0, let's note first of all that the current flowing through here flowing through these two series resistances is V in, so calling it I, is equal to V in divided by 1 over G sub M plus R sub S. Now we have then that V out is equal to negative I times R sub D. But I is that, so we get then that V out is equal to negative V in divided by 1 over G sub M plus R sub S times R sub D. So we can now calculate AV0, which is just V out over V in, should have pointed out without the load resistance, is equal to then just negative R sub D divided by 1 over G sub M plus R sub S. Removing the compound fraction, we get then that this is equal to negative G sub M R sub D over 1 plus G sub M times R sub S. It's useful to compare this open loop or open circuit gain with that of the open circuit gain of the common source amplifier without the source resistance. You'll recall under those circumstances that A sub V0 was equal to negative G sub M times R sub D. We see here then, here's the open circuit gain with the source resistor. This is the open circuit gain without the source resistor. You'll notice that the open circuit gain with the source resistance is less than that of the common source amplifier without the source resistance. And the amount that it's less than is, or this amount is divided by this 1 plus G sub M R sub S term. And you can see that if R sub S equals 0, the gain, the open loop gain for this circuit that we're considering, would be the same as it is for the common source amplifier without the source resistor. As we've seen in the past, this negative feedback does then, I guess the price of the negative feedback is that we have a reduced amount of gain available to us. Finally, the gain with the load, A sub V, well, the load is connected, and it turns out that the load is just in parallel with R sub D. So A sub V then is this same expression, only now we have R sub D in parallel with R sub L, or A sub V is equal to negative G sub M R sub D in parallel with R sub L divided by that 1 plus G sub M RS term. And finally, because V in is equal to V sig, again, that's the result of the infinite input resistance, there's no voltage division taking place here, then the overall gain, the total gain G, is just equal to A sub V.